Okay, so, well, it's 3 o'clock for me in morning at the moment, so if I'm slightly incoherent, you should stop me and ask me to clarify whatever I'm saying.
Clarify that.
I have no idea. What did I just say? Okay, so the question I asked in the title here is about, the basic question here is really, well, how much do we actually know about the dynamical evolution, dynamical history of the solar system? Did we always have only 4 giant planets, or could we have actually at least do something in the process of the evolution of the system? So I'll very quickly go through some points. First, I'll give you an overview of some of the kind of the basic evidence for the fact that we think that why we think that the giant planets have migrated, the various migration models that people are now working on, and then I'll go through some simulations where we try to figure out the probability of success for the different models, right? And in particular, the constraints that come from the orbits of the planets, and something that's new that we are working on using the obliquities of particularly Jupiter and Saturn, so the spin axis tilt of Jupiter and Saturn. Okay, so evidence for migration. Probably the simplest and strongest is from the Kuiper Belt objects. And so these are all the objects that are outside the orbit of Neptune. Of course, the most famous one was Pluto, that was discovered in 1930. And then it wasn't until 1992 when we started finding many more, and I think by now there's well over 1,000 of these objects known. And you can think of all of these as objects that were left over from the formation of the outer solar system. So here's a plot showing you, I actually did this a few days ago, so this is the semi-major axis versus eccentricity of all the known trans-Neptunian objects. And you can see here, again, the dashed lines here indicate places where you are in mean motion resonances with Pluto, with Neptune, right? So Pluto is this blue dot here, which is in a 3-to-2 resonance with Neptune. And you see that there are, in fact, many other objects in different resonances. There are many in the same 3-to-2 resonance. These are all collectively known as Plutinos. And then you have other resonances like 2-to-1, 5-to-3, etc. And the fact that you see all these Kuiper Belt objects in resonances is a very strong argument that Neptune has moved outwards. Right? So I guess no one has really talked specifically about capturing the resonances, but the general rule is if you want capture, you need convergent migration. The period ratio has to approach the resonance from larger than the period ratio. Right? That's the usual rule. And so the idea is then that Neptune was moving outward at some point, and then some of these things that were in the Kuiper Belt were then capturing the resonances. And from the eccentricities of the things in, say, the Plutinos, you can actually estimate how much Neptune has moved. And so in the simplest case where Neptune is just moving nicely outward, you can estimate that Neptune has moved by about 7 AU to get to eccentricities of the order of 0.3. So I'll go through the different models. So the one that I just said is something called a smooth migration model, which is say basically all the planets were moving smoothly. And then I'll go through a few other different models. So the first one, in fact, was a model that was already discussed back in the 1980s. So before we even know that there was really a population of Kuiper Belt objects. And so the basic question here was just, well, we know that you have the 4 giant planets. The protoplanetary disk probably didn't stop at Neptune. So there must be other planetesimals left over after the formation of the giant planets. So what Fernandez and Ip asked was basically, what happened to the planets if you let the system evolve? And the general effects is that the scattering of planetesimals caused Saturn, Uranus, and Neptune all moving slightly outward, and Jupiter moving slowly inward. And in that model, they were thinking about a system where, so this, by consequence, means that the initial solar system, outer solar system, must be much more compact than what we started with, than what we see now, right? Because the Uranus, Saturn, Uranus, have all moved outward. And the masses that has been estimated that you need to move the Neptune by about 7 AU is a disk of planetesimals that's about 50 Earth masses. And then almost 10 years ago, I guess next year's the 10th anniversary of this thing called the NEAS model. And this was published in a series of papers by Saganas et al. And their idea was similar, except that they said, well, what happened if Saturn even started closer than what people were thinking about? So particularly, if the period ratio between Jupiter and Saturn was closer than 2 to 1. Okay? And all the ice giants would be within Uranus and Neptune would be within 18 AU of the solar system from the sun. And this is the sort of thing that they find. Right? So a similar idea, you basically have scattering of planetesimals causing the orbits to move. And the key thing that happened here is that Jupiter and Saturn cross the 2-to-1 resonance, which cause eccentricity perturbations, and you make Saturn eccentric, and then because Uranus and Neptune are much closer to Saturn, the whole thing becomes unstable. There's a period of scattering, and then eventually Uranus and Neptune, in this particular case, they swap locations, eventually end up in their current orbits. Now, this was very popular because it solved a few different problems, but people didn't like it for different reasons, one of which was why did it actually start with this particular initial conditions. And in particular, it ignored the problem about migration due to interaction with the protoplanetary gases. And this then led to the next generation of the Nice model, which is something we refer to as the Resnick-Nice model. And they basically were thinking about the effect of the gas disk on the migration of the giant planets. And so in that stage, again, Jupiter, so you think about Jupiter and Saturn, they will be all moving due to interaction with the gas disk. And in particular, you could actually capture them into a resonance, 3 to 2 in this particular case. And then the nice thing about the 3 to 2, if Jupiter and Saturn were in the 3 to 2, they would actually be almost stationary. They don't actually move inward or outward. And then the idea was, well, you just do the same thing and repeatedly put in the other 2 ice giants. And you eventually ended with all 4 giant planets in a chain of resonances. So Jupiter and Saturn in 3 to 2, Saturn and the inner ice giants in 3 to 2, and the pair of the ice giants in 4 to 3. That's one of the combinations. There are other possible combinations of resonances. And so then you see something similar again of the evolution where you have divergent migration due to scattering of planetesimals, eventually ending up with things in the right orbits, right, hopefully. Now, what happened is, and I'll show you more statistics, is that people started doing more numerical simulations trying to figure out how successful this model is. And it turns out that you see that there are these events here, there are encounters between the planets, and it's actually very easy to eject one of the ice giants. Okay, and it's more likely to eject an ice giant than actually having all 4 survive. And then if you think about other constraints from the orbits that you need, and I'll talk about those, then it's almost impossible to match the solar system from the rest of this model. Okay? So, then it leads to kind of a natural question idea. Well, if it's easy to lose this ice giant, why don't you start with 5 planets? Okay? And so, more recently, starting around 2011, 2012, there were a couple of papers talking about the idea, well, what if we started with 5 planets, 1 extra ice giant, and then in the process of this evolution, ejected 1, okay? And then you can ask, would this actually work better than the rest of the Nice model? Okay? And so I'll talk specifically about 2 possible combinations. Again, the idea here is that all the planets started in resonances. And I have actually worked on 2 different ones. One is a compact configuration, kind of like the Resnick-Nice model, 3 to 2, 3 to 2, 4 to 3, and then the outer two ice giants are also in the 4 to 3. And then you can also have a more loose configuration with 3 to 2, 3 to 2, 2 to 1 between the inner 2 ice giants, and then 3 to 2 between the outer 2. Okay? So here's kind of the possible type of scenario situation that we see. All right, so here's one that you are in fact left with only 4 planets in close to their current orbits. And you see here they started with 5, so there are Jupiter, Saturn, 3 ice giants. And in this particular case, you eject the middle one, right, during this encounter phase. Okay, so what are the constraints that, so if you have all these different models, how do you try to test them? So you need to find some constraints. And the constraints people have been working on mostly are in terms of the orbits. Okay, so of course, again, you need to see that you have to have the current system, so you are left with 4 giant planets, Jupiter, Saturn, and 2 ice giants. You also want the planets to have semi-major orbits that are similar to the current ones, so different people have slightly different criterion. The one in the simulations I'll show you will require the planets to be within about 10% of their current semi-major axis. One of the conditions that people have found is necessary is something called a jumping Jupiter scenario. And it's the idea that, in fact, the period ratio between Saturn and Jupiter has to jump through this range from 2.1 to 2.3 in a very short time scale. Because if Jupiter and Saturn pass through that period region very slowly, then you have trouble with the inner solar system. So you could actually make the terrestrial planets having 2 orbits that are too eccentric, and there are also secular resonances that pass through the asteroid belts, and you basically screw up the entire inner solar system in terms of being consistent with what we see now. And the last thing, I guess Scott defined these longitudes of periaps. So if you look at the current system, the longitude of periaps, the difference between Jupiter and Saturn, so basically the angle where Jupiter and Saturn periapses are pointing, and the difference between the 2 angles is circulating, so it goes around 360 degrees. It's not oscillating around a fixed value. So those are the criterions that one would like to match in terms of orbits. And the new ingredient that I'll talk about here is the obliquities of Jupiter and Saturn. Okay, so obliquity specifically is defined as the angle between the spin axis and the normal to the orbit. Okay, so, and hopefully you all know that. Saturn has 27-degree obliquity, and Jupiter has about 3 degrees. Right? The Earth is 23.5. Now, it's long been a problem trying to figure out how to explain the obliquity of Saturn, because it is a big planet, and it's very difficult to explain it if you try to tilt it by collisions, because then you need a really big object to collide with it. And one of the really neat ideas came about in, I guess, 2004. And this was a scenario suggested by Ward and Hamilton. And what they noticed was, so the spin axis of course precess because of the torque from the sun, but the orbits also precess. And what they noticed is that there's a coincidence between the precession period of Saturn's spin axis and one of the orbital precession frequencies. So I don't know if Scott will be talking about eigenfrequencies, but basically there's one eigenfrequency which is related. So you have the planets which are all inclined in orbits, and so they would be precessing, retrograde direction. And there are different, so you can decompose that problem into eigenfrequencies. There's one eigenfrequency which is associated with Neptune, and that frequency is very close to the spin precession frequency of Saturn. And so the idea that they came up with is to use something called a spin orbit resonance to tilt the spin axis of Saturn. And the other thing that's also very interesting is that even though Jupiter's obliquity is only 3 degrees, its spin precession frequency also happens to be close to another eigenfrequency, S7. And but obviously it doesn't have a large obliquity, so it wasn't tilted by the spin precession frequency, spin orbit resonance with S7. So these are 2 things to keep in mind. You need to tilt Saturn, but you better not tilt Jupiter. So let me just very briefly explain this secular spin orbit resonance. So again, as I said, so the idea here is you have a k, which is a vector which is normal to the invariant plane, so it's actually something fixed, right? And then you have the spin, which is precessing around due to the torque from the sun, and the orbit is tilted from the invariable plane. And it is also precessing due to the perturbations on the other planets. So these things that are referred to as Cassini states are the one where the orbits and the spins are precessing in the same speed, going around this vector k. Right? And there are, depending on the obliquity and the spin precession, and the inclination of the orbits, you could have either 2 or 4 of these so-called Cassini states. Okay? And the one that we're talking about is something called Cassini state 2. Right? And the idea here is, right, so alpha is the spin precession frequency, S is one of these eigenfrequencies, and you cross this resonance when the ratio is about 1, so an absolute value. So the idea is that you started from this side, you slowly, so one of the ways you can go in this direction is decrease the precession frequency, so the eigenfrequency, S, and then this is alpha over S, so it's increasing in that direction. And you see that Cassini state, this is the obliquity, and you see that it started at very small on this end. So if you systematically decrease S, you will be moving in this direction. Right, so when you cross about 1 or -1, that's when you are get caught in the spin orbit, secular spin orbit resonance. So this was the idea that you started with Saturn having very small obliquity on this side. You slowly decrease S, and then you end up on this side with Saturn somewhere over here with 27-degree obliquity. Okay. And one of the ways you actually could decrease S would be having Neptune and Uranus moving out. Okay. And the other key thing to mention here is that it depends on the time scale on which you change S. Right? So if you change it too fast, you wouldn't be able to stay in the resonance and get out of the resonance. And so there's a constraint on how fast the time scale, the S could be changing for you to actually be captured to the resonance. Let me skip that particular thing, which is basically about the constraints on the time scale. Okay, so I've done a couple of different types of simulations in trying to see if we could actually tilt Saturn without tilting Jupiter in all these different migration models that I just mentioned. I'll very briefly talk about a particular set of simulations which are secular in the sense that these are not full n-body calculations. And so I basically force the planets to move on some specified time scale so I can control the problem. And then the planets interact through something called secular interactions. And I also included the spin interactions, right, spin evolution. We then do a bunch of full n-body simulations using one of these symplectic integrators. And the new thing here is that we also included spin evolution in this code. Right? And the calculations that we did was with, and I guess I forgot to mention at the beginning, this was work done with Ramon Brasa. And we have done a lot of simulations with a disk of planetesimals with 3,000 planetesimals. And each of the models that I mentioned before, we did over 1,000 simulations. So I think this is by far more than anyone else has actually done. Right? So most people have done maybe 100 at most, and the statistics is not very good. Okay, excuse me. So this is from a secular simulation. Right? So basically, again, I'm just forcing all the planets to move. So this is semi-major axis, the perihelion and aphelion. These are the inclinations of the orbits. This is the obliquities. And down here are those different frequencies. And you notice here, red is Jupiter. It got tilted to over 5 degrees. And then Saturn only maybe 6 or 7 on average, didn't get beyond 10 degrees. Okay? And so you already noticed that there's a tendency here that you can actually easily tilt Jupiter to bigger than the surface obliquity, and difficult to tilt Saturn to something to the amount that you see in the current system. And the problem here, and I'll highlight these points here. So the different color curves are the spin precession frequencies of the 4 giant planets. These are the 3 eigenfrequencies. And you notice here that this S8 is higher than all of the spin precession frequencies. It has to pass through Jupiter. As Neptune moves out, it has to actually pass through Jupiter's spin precession frequency before it gets to Saturn. And you can see right here, that's the point when you actually tilt Jupiter. And then you see here, when it encounters the spin precession frequency of Saturn, that's when you tilt Saturn. But you don't tilt it sufficiently. Again, the other thing to notice is that the spin precession frequency of Jupiter is now close to S7. So if you somehow cross it, you have a problem, because you can also tilt Jupiter by crossing the S7. So the bottom line here is, so we did a whole bunch of simulations, these secular simulations where you can control the time scale of migration. And what you see, as you saw in that plot, is the general pattern that you actually generate a Jupiter obliquity comparable to Saturn. Right? So it's all these different dots. And this is the actual solar system. Okay. So we see that there are potentially some problems from the secular simulations. But of course, this is a contrived problem. Because as you remember, right, so in any of these NEAS models or the 5-planet models, there's a phase of encounters when the planets can move very rapidly. Right? And so one possibility is maybe you bypass the problem by having Jupiter having the Jupiter and S8 passing through each other very rapidly during the encounter phase, and then having a very slow migration at the end, so that Neptune and Saturn ends up in this secular spin-orbit resonance. Okay, so then that means you really have to do n-body simulations, which is what we did. Okay, so I'll show you different results here. So again, these are plots showing you obliquity of Jupiter versus obliquity of Saturn, linear and logarithmic plots. So this is for the resonant NEAS model with 50 Earth mass disk. And the color coding here is for the black dots. These are the ones that have all 4 planets at the end. The blue dots are the ones that actually have the semi-major axis within 10% of the current one. And the red dots are the ones that actually satisfy all the orbital constraints. As you see here, there are no red dots anywhere near the actual solar system. Right? And all the red dots have either Jupiter and Saturn comparable or Jupiter even bigger obliquity. And so, and you see that there are very few red dots here out of over 1,000 simulations. Okay? So this is not very good. Right? So that's why we then look at the 5-planet models. Okay, so here's one, which is the compact red 5-planet configuration with a 35 Earth mass disk. You have a few successes now in terms of having blue dots, which are close to the red, the actual system, but again, no red dots. Okay, the red dots are all again comparable Jupiter, Saturn, or even bigger Jupiter. And this is the loose one. You have many more red dots in this set of simulation compared to that one. But again, well, actually, maybe even worse in this case, that there are actually no red dots and actually very few blue dots anywhere near the actual solar system. Okay. So the last thing we tried was this one, which was a compact 5-planet configuration that had a heavier disk. This one looks slightly promising. Okay, so you now see that there are many more red dots, and some are in fact kind of in the region where you might want to try to reproduce the current solar system, right? But still only a handful. So let's say if you're really generous, you say anything that have obliquity less than 10 degrees for Jupiter and about 15 for Saturn. There may be 1, 2, 3, 4. I think there are 4 of these systems that are red dots. Okay. So this is telling you that in fact, the idea here is that just looking at the orbital constraints do tell you a lot, but actually if you really want to, if you actually include the obliquity constraints, then even harder. Right? So it's very difficult to reproduce the current solar system with any of these models. And the only kind of successful one is this one. Okay, so now I'll show you, so I haven't shown you these plots in the n-body simulation. So here's one, which is from the evolution of the system from the 5-planet configuration. This is one of the unsuccessful ones. Right? So you do eject 1 planet, so you are left with 4. There is a jump in the period ratio between Jupiter and Saturn. But what you notice is that, again, here you have Jupiter having obliquity much bigger than Saturn. The reason here is slightly different. Right? So you do avoid the problem of S8 crossing Jupiter. Actually, it's not even crossing Saturn, so that's the problem. You're not generating large enough obliquity with Saturn. But the S7 did get close enough to Jupiter's spin precession frequency. And you ended up with a really large obliquity for Jupiter from the spin orbit resonance between S7 and Jupiter's spin precession frequency. This is one where so this is the successful case, right, where you do not generate a very large obliquity for Jupiter, but a large one for Saturn. Okay, and here you see that again you avoided the problem by having this very rapid change in S8. But then right at the end here, that's when it's approaching alpha S. So this is kind of the ideal situation where you have managed to get Saturn into a spin orbit resonance, but S7 is sufficiently far from the spin precession frequency of Jupiter that you don't increase the obliquity of Jupiter. Okay, so this is a summary table of all the different runs that we did. Okay, so this is the resonant Nice model, the two compact the compact 5-planet and the loose 5-planet configurations. This is the 5-planet with the heavier disk. And the statistics here, this is the fraction that actually have 4 planets. The fraction that satisfies the orbital semi-major axis would be 10%. And this is the fraction that satisfies all of the orbital constraints. And these are the fractions that actually satisfy the obliquity constraints. Right? So as I showed you before, if you want to satisfy all of the orbital constraints, it's actually the probabilities are pretty low, especially for the rest of this model. It's better with the 5-planet model, especially with this one, but none of these produce anything that look like the current solar system in terms of obliquities. And then the only kind of successful one is this one, right? There's about 6.6% probability of satisfying all orbital constraints, and we have a few cases out of 1,200 simulations that actually also have obliquities that look like the current solar system. Okay, so what I'll summarize here is that so some of you who work on solar system dynamics might have heard of the Nice model. And it turns out, again, that the basic lesson in the last couple of years is that it is very easy to eject one of the ice giants. So that led people to think about the possibility that the solar system originally started with an extra ice giant, this resonant 5-planet model. And hopefully I convince you that the obliquities of Jupiter and Saturn do tell us a lot about, can constrain a lot about the orbital history, right? Because there are 3 different things going on. You have the S8 that has to cross Jupiter's spin precession frequency, and then it has to reach Saturn's. And then you also do not want the S7 to cross Jupiter's spin precession frequency. So those are kind of not easy to match, all of those. Okay, so and hopefully you saw that both the resonant Nice model and some of the 5-planet models do not reproduce both the orbital and spin properties. The only one that kind of worked was this one with a heavier disk. But even in that case, if you go back to this plot, right, you notice in terms of the red dots, it's actually much more likely you generate too big a Jupiter obliquity. So most of the red dots actually have large Jupiter obliquities. So then, again, you have a problem. And I think this is basically fundamentally a fact that the current solar system, right, the spin precession frequency of Jupiter and S7 are very close together. So if you just move the orbit slightly, it's very easy to actually having them end up in a resonance, and then you will tilt Jupiter by a large amount. I guess I'll stop there.
Additional constraint in the inner part of the solar system when you go through this, right? Because that could also affect the eccentricity of the Earth.
Right, I think that was the jumping Jupiter criteria.
Yeah, but then, just in this initial state, you check whether you could also change this obliquity of some of the terrestrials.
Ramon has that idea. We're kind of starting to think about it, but we haven't checked it out.
Saturn is currently not in spin orbit resonance. You have to break it out of those.
I don't know that we know for certain. I think I think it depends a little bit on what you believe in terms of the moment of inertia. There are these papers by Hallett et al. Claim, I guess they have a slightly different measurement of rotation and then the moment of inertia, and that actually does put Saturn out of the resonance. So if you believe that measurement, actually Saturn would be out of the resonance.
Is it possible that I'm out of resonance?
There are situations where you will be out of resonance. I don't think we have actually checked all of them, even with high obliquity, whether the Saturn remain in resonance. occasionally you get a situation where it was getting into the residence, but then eventually escaped. So you would actually have it ending up with larger frequency, but not in the residence.
I'm a little confused by what you mean about low probability. I mean, there's only one solar system,
Yeah.
so even if this happened only once in 10 to the 10th simulations, if it happened, and maybe that's the one that is us.
Well, I think this is always a problem with these, at what probability are you willing to live with? You know? So I think it's up to, I don't know that how one can quantify. I think it's almost a personal judgment
Okay, but
about
low
at what probability do you actually feel comfortable with.
But the low probabilities that you're getting of matching both constraints with 1,200 simulations. Naively, it seems to me that doesn't mean anything because we've only got one solar system and maybe we formed in a low probability event.
Sure, but so then you will have to say that it is a low probability. Sure. So I'm quantifying the probability here. So then I guess it's a question of whether one is comfortable with a low probability.
One way you could maybe fix that, or at least put a constraint on it, is by limiting the number of planets so that you can check that the limit of the number of floating planets.
So that's
some limit.
right. So
You check a Jupiter for every solar system, you check 10 Jupiters for every solar system, then you would.
but I think that is requiring you to have some idea about how things works for other planets, not just for our own solar system. What's the probability of ejecting planets?
Yes.
Planetary formation in general.
Yes, but that's what you apply when you say that you want a high probability scenario. Otherwise, you can use Scott's argument and say here's the one that is special. Times the -10 probability. If it's a 3% probability, then there must be many others that look like.
Well, so maybe I can rephrase it slightly stronger, which is that for things like resonance model, we couldn't, out of 1,200 simulations, there was nothing that matched both of our constraints.
Okay, so let me rephrase mine a little more strongly. Suppose I build a whole bunch of simulations with planets of different masses, and I don't run them at all. I don't do anything. I just say, gee, only 1 out of 10 to the 5th of those has a planet that's the mass of Saturn and another one that's the mass of Jupiter. Right? But that's basically what you're doing.
Maybe the way to go around it is to say that there are a certain number of special circumstances. The probability of getting all of them in there is measure zero, no measure. In a sense, you can try all of the possibilities here to explain, let's say, the obliquity of Uranus, and then try to match that with Saturn and Jupiter at the same time, and then you need special circumstances. But if there are circumstances that there's an overlapping region that you can't satisfy both, I think it's still a viable investigation as a proof.
That's why
I think that's similar to what I said earlier, right? Which is that for some models, we haven't even found any success at all, right? So it's only one set of models where we have some successes.
But the problem with this model is it's refining at all times. I mean, it's continually trying to, put in new ingredients to explain the solar system because they're too ambitious. They're trying to explain every sort of little specialty in the solar system. And when you do that, then you just introduce this house of cards. You just add on.
I always thought you were too ambitious.
Not compared to you.
Not compared.
I only go after the big ones.
Also surprised to hear Scott be so anti-computer.
So that's
I have a very quick question on that. The probability depends on the duration of the simulation. You make the longest problem.
These have all been run long enough that we know, I think we know pretty sure what the end state is.
How long is it?
I have to check. I think we've run, I think it's something like 500 million years, but I have to check. But actually, you might be able to tell from some of these simulations. So this one was to 300 millimeters. But I think it was actually longer, I think it was just farther than 300, but at least 300 millimeters. It's to the stage where there are very few planetesimals left. I think that's the key. Yep.
Did you try to see what the effects there are on things like asteroid belts?
Effects on,
Like have additional particles to see how these changing residences affect the distribution of particles in the asteroid belt or kind of some distance.
right. So some of that, so you notice that I have these, the constraints about this jumping Jupiter again, that has something to do with the asteroid belt. I don't know anyone has actually worked on that in terms of the 5-planet models, but certainly for the NIES models, that has been looked at, the effects of the evolution of the NIES model, how that affects the inner solar system, the asteroid belt, and sure.
That was why it was proposed at the first place for LHB.
Yeah, sorry, yeah.
That's all to do with the perturbation of asteroids.
Right. Well, it's both the asteroid belts and actually the cometary, the Kuiper belt objects, right? So because the influx, I think there are comparable amount of influx in both. So the whole idea about the NIES model, or something like this, is that there is a violent event that happens at a particular time, much later than the formation of the planets. And there's something called the late heavy bombardment in the solar system. And one of the reasons why people like the NIES model was that there's a sudden event here which triggers the influx of the
Well, could a fifth planet somehow make the LHB happen earlier or later?
I think it's the same situation here, because it's basically encounter phase when you inject one of the nitrogen.
I think we should probably stop running a bit late. If you found any of the talks interesting, we have now time for more interaction